Welcome to the technical seminar. My name is Scott Earley and I'm the head of production here at UniKLasers. Today I'm going to be demonstrating our Duetto 349 CW UV platform. The setup procedure for the laser is very straightforward. Begin by placing the laser head on your bench and clamping it down using the clamps shown here. You would then plug the laser head into our thermoelectric chiller. Once the chiller has come to temperature, we would then, using our graphical user interface, switch the laser on. The laser head is connected to a laptop via a USB cable, and to switch the laser on is simply a case of clicking a button. Warm-up time for the system is around 10 to 15 minutes. The performance of the system is inherently very stable. As you can see on the oscilloscope, the laser is very stably single frequency. On the power meter, you can see that the laser is running at approximately 57 milliwatts, and if you have a look at the screen, you can see the wavelength of the laser is at 348.85 nanometers. And if we have a look at the long-term stability graph, the system's been running for a couple of minutes, and you can see that it's stable within the resolution of the wave meter, which is showing at 10 centimeters per division. As you can see from the hole spacing on our optical bench, the footprint of the laser is very small, allowing for easy integration into any setup. Our lasers have been designed to maximise operational lifetime. We offer scheduled maintenance which we can perform remotely, so that you don't have any unexpected downtime. Our lasers are manufactured here in Edinburgh and can be offered on shortened times. Hopefully this video has provided a useful overview of our new Duetto platform. If you have any questions, please contact info@UniKLasers.com.
Good afternoon, everyone. Welcome to our short technical webinar. My name is Johnny Bray. I'm head of sales here at UniKLasers. I'll be giving you a short presentation introducing our company and our products and some of our applications. If you have any questions throughout the webinar, you can use the chat function, and we'll have an opportunity to answer those questions at the end. To give you an introduction into who we are, UniKLasers is a small but growing photonics company based in the capital in Scotland. We're currently around 20 staff. Just last year, we moved into new premises that you can see in the picture here. We increased our production and our optical capacity, and everything that I will be presenting to you today is designed and manufactured and produced in our facility in Scotland. So we're a leading edge photonics company, and what we specialize in is the development and production of continuous wave single frequency DPSS lasers, diode pump solid state lasers. And what our products are based on is our patented Brams Technology platform. This is something I'll be explaining to you in a few slides' time. But what it allows us to do is to produce very narrow line width, single frequency lasers at a very small footprint with extremely high stability and extremely low noise. Historically, we've been a research company. We were founded about 8 years ago by Professor Fedor Karpushko. Professor Karpushko was previously the deputy director of the Academy of Science in Belarus, and he's been involved in lasers since their invention by my man many years ago. He's been cited on a little over 40 laser patents, And this laser patent of Brams Technology is the founding technology on which UniKLasers is based on. We have a wide research and funding network. So we work with commercial partners, people like Fraunhofer and Teledyne. We have good funding support and research support by large national bodies, people like Innovate UK and Technology Scotland. And then we also have a wide academic network as well, working with people like the University of Birmingham or the University of Strathclyde more locally. And all of these elements together have allowed us to develop and implement this Brams technology into our products. Brams technology is a way of restricting the number of modes that are possible within a laser cavity that allow us to have direct access to lower wavelengths with less nonlinear steps, and also to have very high efficiency in our wavelength conversion. So what you can see here is a simplification of a laser cavity with a gain media placed in between two reflectors. We can add a nonlinear crystal if we want to access different wavelengths at a higher energy regime, but that is of course an optional step depending on the frequency of laser. But Brams technology is this section on the right-hand side where we combine a volume Bragg grating. A volume Bragg grating restricts the number of reflected modes from the gain media in the cavity. And we combine this with a Michelson interferometer, which allows us to tune these reflections to just a single mode, allowing us to operate a very narrow line width or at single frequency. We then use a tilt locking mechanism, which allows us to control the cavity length for things like thermal changers, and we lock into this frequency in this way. So overall, this gives us a unique method of single frequency generation at very high efficiency and high power. We have very high stability. There's no mode hopping. The spectral stability is rock solid over a long operational time. And it also gives us more direct access to different wavelength outputs. So some of these I will introduce to you as part of our product range. So to give you an example of how we implement this technology, I'll start with our Solo 1064. So this is a small solid state single frequency laser operating at 1064 nanometers. We can produce very high power. We have up to 2 watts with this very high power stability over a long range. But in particular, what makes this laser unique is the combination of very narrow line width, less than 500 kilohertz, with this very high output power of up to 2 watts, all contained within a small solid state footprint. On top of this, we can also produce very high beam quality, so excellent M squared, excellent beam shaping, and overall small beam diameter and low beam divergence. As we move down through the wavelength range, I'll show you that we managed to maintain these specifications. So the specifications on the left-hand side are now for our 640 laser, working up to 1 watt in output power. But to give you an idea of how this relates into real-life performance, we have a data down in the bottom right-hand side that shows over an entire day. So this is demonstrated over 24 hours. We have a power stability of less than 1% and a wavelength stability of less than 1 picometer. These are under the stated specifications, which act as a baseline guarantee for our products. We also have excellent beam quality. It's a very high ellipticity and a nice Gaussian shape in both axes across the beam. We produce these lasers down at 532. So you will see as we step through our different wavelengths and different products, the number of applications that are highlighted for each laser change as we go through. As we move down through the wavelengths, we have higher energy, but of course we move into higher spatal selectivity as well. So the lasers are ideally suited for applications where there is a high energy selectivity, so things like Raman or holography or Brilliant or interferometry, but also for areas where a high spatal selectivity is required as well, things like semiconductors or lithography or microscopy. To give you an idea of how our lasers are used, they are used both in academia and in industry. Here is one of our customers in Germany. You can see our laser is integrated in the bottom right-hand side of the picture. It is integrated into a confocal microscope that is being used for Raman spectroscopy. So the single frequency operation gives very good control through the microscope, both in the X and the Y, but also in the Z axis as well. It's these types of applications that lasers are ideally suited for. The other part of our business that I have not mentioned yet is our quantum technology. So the Brams technology that I am discussing was partly developed and funded by national research projects. Our latest one is one called QT Assemble. This is a project that's led by Fraunhofer, and the concept behind it is to make quantum technology easy to adopt by making sources that can be integrated that have the correct size, so they're very small, they are low weight, they do not use much power, and they have high reliability. So the national funding that we receive is to allow us to make these lasers smaller, more robust, and more reliable. And it's this technology that we implement into our quantum laser series, the Solo 81342, the 780.24, both used for rubidium transitions, and the Solo 698.4 and Solo 689.4 for strontium. It's this technology that allows us to produce our entire product range as developed as part of our national research projects. Most recently, we've moved into the UV. So we recently released our Duetto 349 laser series. To give you an idea into our naming convention, you'll notice we have the Solos and the Duettos. The Solos, like the 1064 and the 640, are direct frequency conversions. There's no nonlinear step, whereas our Duettos involve one nonlinear conversion. So you can see in our Duetto 349, we can have direct access to the UV range using just one nonlinear step, as opposed to typical outputs, something like a 355, which would be frequency tripled from a 1064. This allows us to have high energy efficiency. We have good output power. But again, what makes this laser specific to us is the small footprint, the very narrow line width, and the extremely high stability. I showed you this performance data for some of our other lasers before, but now this is for the Duetto 349, and we're operating over a longer time scale. So now this is continuous operation over 65 hours. And you can see again, we have this very high power stability of less than 1%, and this extremely stable wavelength output, with the wavelength changing just less than 0.06 picometers over 65 hours. The Duetto 349 shares through a few specifications with our other lasers. As with our other lasers, it was designed for integration, so it has a very small footprint. It is connected via USB, and then partly because of the situation with the pandemic, but partly to avoid operational downtime, we also have software control that allows us to remotely connect to the laser for diagnostics. So we do not need to travel to inspect the laser, we can connect remotely via the internet, and we can offer you some feedback or advice or make some adjustments as needed. We also have this very high spectral stability and very high power stability. This removes any fluctuations or changes during your data collection or analysis. Makes the analysis of the data much straightforward. It gives you very high repeatability, and it also ensures a very long operational lifetime as well. And then finally, the very narrow line width gives you this very high selectivity and long coherent length also. Thank you for paying attention to my presentation. If you have any questions, you can put them in the chat function. Otherwise, you can visit our website at www.UniKLasers.com, or of course, you can contact me directly on any of the details shown on the screen just now. Thank you very much for your attention.